In this lecture, we will discuss about the isothermal elasticity and adiabatic elasticity of a gas. Isothermal and adiabatic elasticity of a gas. So you know that according to Hooke's law, the stress by strain is a constant. This proportionality constant is called coefficient of elasticity. So we need to calculate this coefficient of elasticity for a gaseous system, for adiabatic and isothermal processes. So first of all, we will consider a perfect gas maintained at a temperature T, pressure P and volume V. The gas is compressed by increasing its pressure to P plus dP and volume is decreased to V minus dV. So change in pressure is dP and change in volume is minus dV. Then what we need is the ratio of stress by strain in an isothermal process. So for that, first of all, write the expression for stress and strain. The stress is nothing but force per unit area, that is the pressure applied on the gas. So the pressure applied on the gas is dP. Then the strain is actually the ratio of change in dimension to the original dimension here. Change in dimension is the change in volume, that is minus dV, divided by the original dimension is the volume V. So the coefficient of elasticity of the gas is given by stress by strain, which is always equal to dP by dV with a minus sign into 1 by V. So minus 1 by V into dP by dV is the elasticity. Now let's calculate for isothermal process and adiabatic processes separately. So for an isothermal process, we know that PV is equal to a constant. Then we need dP by dV. So differentiating this equation, we will get P into dV plus V into dP is equal to 0, which implies dP by dV is equal to minus P by V. So isothermal elasticity is usually represented by E theta, which is equal to minus 1 by V into dP by dV is minus P by V. Oh sorry, it is there is a mistake here. Here it is stress by strain. Strain is dV by V, so it is minus V into dP by dV. So here it is sorry for the correction. Minus V into minus P by V, so it is equal to P. So the isothermal elasticity of a gas is given by E theta is equal to the pressure. Now for an adiabatic process, let's calculate what is this adiabatic elasticity. For that, consider the equation of state for an adiabatic process. It is PV raised to gamma is equal to a constant. The differentiating this one, it is V raised to gamma into dP plus P into gamma into V raised to gamma minus 1 dV is equal to 0. So from this equation, if you calculate this dP by dV, we will get dP by dV is equal to gamma times P into V raised to gamma minus 1 divided by V raised to gamma, which is equal to gamma into P. V raised to gamma minus 1 can be written as V raised to gamma by V into V raised to gamma. So this will cancel. dP by dV will be with a minus sign. So minus gamma into P by V. So the adiabatic elasticity denoted by E phi, which is equal to stress by strain. The stress is dP and strain is dV by V, so it is minus V into dP by dV, which is for an adiabatic process minus gamma times P by V. So it is equal to gamma times P. So adiabatic elasticity E phi is given by gamma times the pressure. So from here we can say that isothermal elasticity of a gas is equal to 1 by gamma times adiabatic elasticity, or E phi, the adiabatic elasticity of a gas is given by gamma times isothermal elasticity E theta of the gas. So E phi is equal to gamma times E theta. From this equation we can say that for a similar change in pressure dP, there is a larger change in volume for the adiabatic process. So if you change the pressure in a same magnitude, if the process is adiabatic, then the volume change will be greater when compared to that of isothermal process. So that gives the relation between the isothermal elasticity and adiabatic elasticity of a gas for an isothermal and adiabatic process. So that's all about the first law of thermodynamics and all. Now we will discuss about some other type of thermodynamic processes like reversible process and irreversible processes, and those things will be discussed in the next lecture onwards. Thank you.